welcome back. Okay, so today we're going to talk about kinetic model method. Okay, this is the real thing. Yeah. So, we did these two objectives the last lesson, and today we're going to look at Brownian motion first, followed by the so-called ideal gas law. Okay. Basically, an equation that actually talks to you about E and F. Okay. Especially F in particular. Uh, here. Okay. Now, just a quick recap. We talk about the intermolecular forces, the arrangement of particles, how strong are they? Okay, and then we say that the closer they are, the stronger the force. All right. And then we talk about here. We talk about the phase diagram. Okay, and the graph regarding kinetic model, or rather relating to kinetic model. Okay, and then we say that during melting and during boiling processes like this, they do not have a change in temperature. Okay, the more thermal energy you give to these structures, okay, from solid to liquid to gas, okay, through this process of melting and boiling, we were talking about what happens to the thermal energy. Okay, why does it has a temperature change? Okay, and then I give you a video regarding Brownian motion. Okay, this thing here. Okay, yeah, it's by some biologists, by the way. Okay, not really a physicist. Okay, but we use the model too. Okay, so yeah, good, right? You see how science is interlinked throughout. Okay, so say hi to your bio friends to me. Okay, now in Brownian motion, right? Yeah, you all can watch the video in the link below. Okay, check out below in the description. Okay, there's a link. I want you all to watch that from 1 minute and 10 seconds onwards. Okay, that will give you a rough idea of what Brownian motion is. But basically, in the experiment, okay, we have under microscope, okay, we are able to see smoke particles. Okay, so smoke particles look like that. Okay, now if no one touches the smoke particle, fine. Okay, the smoke particle in the screen are just going to look like this. However, if someone is going to touch the smoke particles, okay, they will move from in a manner like this. Okay, let's say they are arranged in this manner. Okay, uh and they will start to distribute themselves in this manner. Okay, so it seems like someone is touching them. So how? Okay, and that is the entire idea of Brownian motion. Okay, so if you do look at Brownian motion, okay, basically something is pushing it here, something is pushing it here, something is pushing it here, causing these three balls, okay, to eventually move in this manner. Okay, and over here something is going to push them here, something is going to push them here, something is going to push them here, which will cause them to move, of course. Okay, so uh we will want to ask what pushed them. Okay, it's not Halloween yet, so yeah, nothing spooky about this. Okay, and of course under the microscope we realize that we actually cannot see something, and that is called air molecules. Okay, and because of the random motion of the smoke particles, which I'm highlighting right now, okay, they are moving in random. Okay, we can only conclude one thing. Okay, that that the objects hitting the dust particle or the smoke particles are firstly invisible, okay, and secondly moving in random direction. Okay, now there's no fixed direction as to how the smoke particle are going to move. Okay, at one point of time it's going to move up. Okay, at another point of time it's going to move right, it's going to move down, it's going to move left, it's going to move diagonally, north, south, east, west. Okay, anywhere. Okay, it's going to move in all directions. Okay, and therefore there's no fixed position, and that's why we use the word random. Okay, now they are being bombarded by air particles almost constantly, therefore they move. Okay, yeah, imagine someone pushes you to the left. Okay, you're gonna move to the right. Okay, I mean to the left. Okay, if someone pushes you to the right, you're gonna move to the right. Okay, so if something is wrong, hold on. Okay, if oh crap, sorry. Okay, yeah, just a very simple diagram. We have Okay, my pen is not working. Okay, going to try it again. Okay, uh okay, still not working. Okay, it's fine. Okay, I'm gonna pause for a while. Hold on. Okay, now it's working. Okay, so remember in Newtonian physics, okay, in Newtonian physics, when I push something to the left, it's gonna move to the left, and when I push something to the right, it's gonna move to the right. Okay, this is a new position. This is the new position. Okay, and when we look at this, we realize, oh, this is how the smoke particles are moving. Okay, when something pushes it to the right, it moves to the right. Something pushes it to the left, it moves to the left. But this is in random. Okay, so we therefore conclude that air molecules must be definitely moving in random direction, which goes back to our diagram, which is this diagram. We say that air particles are random and they are far apart. Okay, only when you are far apart then can you have the ability to run around. Okay, if you have to draw a circle to determine the radius of space given to each particle, it's huge. Okay, compared to solid. Okay, for solid, I don't even know if I can draw a radius. Of course, we are talking about the radius, the so-called freedom radius. Okay, and you realize that, okay, largest for air, okay, average for liquid, and nearly zero for solid. Okay, now so that is the key idea of Brownian motion. Okay, now the next thing that I want to talk about is with regards to uh, this describing the relationship between motion of molecules and temperature, and if it is possible, we'll talk about the pressure of a gas in terms of its motion. Okay, so same thing, it's still under kinetic model. Okay, I want y'all to for a second forget, no, sorry, forget what I say. Okay, I'm gonna use a sketchbook now. um to describe the relation between the motion of molecules and temperature. Okay, uh okay, the question that we will want to ask is, how does a molecule move so that T increases or T decreases. Okay, and um actually, in fact, I think this is quite straightforward. Okay, it's the same idea as to heat dissipation. Okay, under a similar idea for heat dissipation. Now, when you think of heat dissipation, I want you to think of an example. Okay, for example, running. Okay, so the faster you run, the more friction, uh, the more the friction, right? Okay, faster speed somehow leads to greater friction. Okay, and your energy kind of get dissipated in that manner. Okay, greater friction. Yeah. So in this case, okay, same thing. Okay, the faster the molecule, the greater the temperature. Okay, so slower molecule is a lower temperature. Okay, in fact, if you were to write it, okay, there's this formula saying that Ke of a molecule is directly proportionate to temperature, and therefore half mv square is directly proportionate to temperature, so v square is directly proportionate to the temperature. Okay, this is the relation that we have here. Okay, so the faster the molecule, okay, the greater the temperature. Okay, and this is a very powerful relation. Okay, yeah, I'll do a quick recap in the next video. Okay, in the next video we'll be looking at how the pressure works.